For a long time, digital product design was driven by gut feeling. If a team couldn't agree on a layout, the loudest voice in the room usually won. But A/B testing replaced that subjective guesswork with an experimental methodology. By randomly showing two versions of a digital asset to users, we can rely on actual empirical behavioral data. The goal is simple: find out which version performs better. In website design or app interfaces, performance usually comes down to increasing user click-through rates or driving up purchase conversions. This infographic breaks down why that objective framing matters. Looking at the objective decision-making panel, we see the transition from subjective disagreements to data-backed conclusions. When the numbers show that version B yields a 15% higher purchase rate, the debate is over. This experimental process also allows teams to break products down into individual elements and test them one by one. Instead of attempting to build the perfect product in a single, risky launch, developers can opt for continuous, gradual improvement. But there is a mathematical bottleneck. Trying to reach statistical significance on a minor tweak, like changing a button color, requires a massive amount of traffic. If you are an early-stage startup or running a niche platform, achieving that required volume makes testing a slow, mathematical grind. To solve this inefficiency, the industry has developed increasingly sophisticated models. We are going to map that evolution, moving from the foundational between-subject designs that require massive audiences to high-velocity within-subject tests, and finally to the real-time AI-driven architectures used today. Mastering these varied experimental designs is critical. It is the primary mechanism companies use to manage business risk and prevent financial loss during product rollouts. The standard A/B test is what statisticians call a between-subject design. Visitors are divided into two completely independent groups, and each group only ever sees one version of the product. The problem here is human variance, or noise. You might have one user who naturally clicks everything incredibly fast, and another who reads slowly and hesitates. Because those baseline personality differences are mixed into independent groups, you need tens of thousands of users just to average out the noise and find a clear behavioral signal. To bypass this volume requirement, researchers use a within-subject or repeated measures design. Here, the exact same user experiences both version A and version B. Focusing on the comparison target panel on the right, instead of comparing two separate groups, we compare the exact same user's reaction to A against their reaction to B. Every participant acts as their own control group. This yields a massive mathematical advantage. By using a paired statistical model, we can completely subtract out the user's baseline speed or tech savviness. The individual noise is eliminated, leaving us with a clean signal showing the true performance delta between the designs. Because personal traits no longer skew the outcome, the required sample size drop exponentially. A test that once needed 5,000 visitors can suddenly achieve statistical significance with just 50. This infographic outlines where this method is essential. The panels show ideal use cases: enterprise B2B SaaS platforms testing complex workflows with tiny pools of expert users, or engineering teams interleaving results to rapidly optimize AI algorithms and recommendation feeds. For product teams operating with low traffic or demanding high-precision feedback on micro-interactions, the within-subject approach serves as a statistical fast-track. But exposing the same person to multiple versions introduces a major psychological flaw: the carryover effect, or order bias. Example 2 on this chart illustrates the learning effect. If a user struggles in version A, they learn the button's location. Switching to version B, they navigate unnaturally fast, making B look superior, even if the design is worse. Then there are demand characteristics. When layouts constantly shift in front of a user, they quickly realize they are being evaluated. The moment a user knows they are a test subject, they stop behaving naturally, which severely corrupts the data. On the back end, systematically alternating versions for a single session requires highly complex architecture. Engineers have to build strict exception handling so that if a user hits the back button or refreshes, they don't suddenly get a broken, mixed interface. To salvage the integrity of the data, researchers must use a mandatory statistical solution called counterbalancing to systematically cancel out the sequence bias. If there are multiple variants, this requires a Latin square design. The system systematically rotates exposure order across different groups. User 1 sees ABCD, while User 2 sees BCDA. Aggregating this data mathematically neutralizes sequence bias. Because of these heavy psychological and technical constraints, standard between-subject testing remains much safer for evaluating critical first impressions, provided you have the traffic to support it. When product teams have divergent ideas, they often need to compare 3 or more radically different redesigns at the same time. This is known as ABN testing. But scaling up introduces the traffic splintering problem. When you test 5 variants at once, your user traffic fractures. Each version only receives a tiny slice of the overall base, which drastically increases the time required to reach a conclusive result. Worse, evaluating multiple variants simultaneously inflates the family-wise error rate. The more tests you run at once, the higher the mathematical probability that you will declare a winner based entirely on random chance. Statisticians counter this with adjustments like the Bonferroni correction, which raises the bar for significance, demanding even more traffic to prove a true result. While ABN compares entirely different layouts, multivariate testing, or MVT, takes a surgical approach. It focuses on micro-optimizations, testing all possible combinations of a page's elements to find perfect synergy. Looking at the mechanics panel here, we see the scale of this operation. If a team wants to test 3 hero images, 2 headlines, and 2 button colors, the MVT automatically generates and tests all 12 combinations simultaneously. The true superpower of MVT lies in discovering interaction effects. It can reveal that a red button performs terribly on its own, but causes conversion rates to skyrocket when paired with a very specific headline. Testing every single iteration is a full factorial design, which requires colossal traffic. For most companies, the solution is fractional factorial testing, a mathematical compromise where only a strategic subset of combinations is tested, and algorithms deduce the rest to save time. Traditional testing is incredibly rigid. You spend a designated period sending half your traffic to a potentially losing variant, wasting time and revenue just to gather data before you can deploy the winner. Multi-armed bandit algorithms destroy that 2-step barrier. They continuously learn and deploy winning variants at the exact same time. This visual illustrates the explore and exploit dilemma. The system sends a small fraction of traffic, say 15%, to explore new variants. The moment a clear winner emerges, the algorithm instantly tips the scale, routing the vast majority of traffic to exploit the winning design. Think about an e-commerce flash sale on Black Friday. You cannot afford to run a standard 2-week test during a 24-hour event. A bandit algorithm finds the optimal layout in the first hour and automatically capitalizes on it for the remaining 23. The trade-off is analytical depth. Bandits are built to maximize immediate metrics, like raw clicks and revenue. They will tell you exactly what is winning right now, but they are terrible at telling you why. Ultimately, multi-armed bandits are essential for exploiting short-window opportunities, where waiting for strict statistical certainty would result in lost revenue. Up to this point, every methodology we've discussed operates on the logic of selection. An algorithm evaluates a finite set of alternatives, A, B, or C, that a human planner prepared in advance. The integration of generative AI rewrites that logic. Frameworks like HyPERA, hyper-personalized experimental research by AI, move past simple selection and enter the realm of creation. The system synthesizes custom alternatives in real time that have never existed before. This is an evolutionary mechanism. By continuously reading user behavioral patterns, the AI engine spontaneously mutates the front-end code, imagery, and text without human intervention. Rather than selecting from 3 pre-written push notifications, the system synthesizes the user's location, the weather, and their search history to instantly generate a bespoke message and image tailored precisely to that exact moment. Content platforms achieve this by mapping granular behavior. For a user who reads meticulously, the AI renders a calm, text-heavy layout. If the next user scrolls fast and engages mostly with images, the AI instantly restructures the exact same article into a dynamic gallery-style UI. Feed algorithms like YouTube and TikTok utilize this concept continuously. They deploy subtle exploration phases to probe for changes in a user's taste, and then fluidly shift the content weights in real time. Educational apps do this with difficulty curves. If a learner struggles with a grammar concept, the system instantly alters the question style and lowers the friction, constantly evolving the application to match the user's exact proficiency level within a single session. The goal of optimization has evolved. We're no longer trying to find the best design for an entire customer base. The new objective is to create the most optimized, highly targeted experience for one specific user, exactly when they need it.